All right, we're recording. So I wanted to finish off the attractiveness thing to make sure we understood where that was headed. Because when I watched the tape, the recording, I realized I didn't sort of wrap it up. So if you remember, we were discussing or going through the debate by luminaries in the field when a question was posed on a discussion board some years ago. How do I represent the attractiveness of a product, or a classic case is of a city. This topic was raised a lot in the urban dynamics literature after the book came out. People are attracted to a city in Jay's model because of jobs and because of housing. And so, well, how do you model the attractiveness of something, a city, a product, whatever the case may be? And there was a whole debate about that and what have you. What was interesting is, until I read that, I didn't realize that urban and regional economists used gravity models, and they're modeled after Newton's laws of attraction, right, from gravity. I think system dynamics is better, but at any rate. So that's intertwined here with allocation, because if something is more attractive, if you will, attractive, quotation fingers, it can often get or should get more of a resource, a scarce resource, right? So they're kind of intertwined concepts. So in that debate, just if you'll remember, we were talking about how these luminaries were debating the best ways to do it. And there's very simple ways to do it. And I showed some of them over here, Mike Bean's method, and the most simple method that's very, very commonly used. But they have their flaws. And Dave Peterson would go on and on about, here's where they fail. For that matter, here's where other formulations fail. And, you got to use the alloc P function in Vensim, which is based on the Woods algorithm. And if you remember, George Abacus, a very good modeler, said, no, you want to use Daniel McFadden's discrete choice formulation, and he won the Nobel Prize in economics for that. McFadden was interested originally in transportation issues, like what highway do I pick to go to work in California, and what's the most attractive route, to take. And so Sturman finally weighs in and says, well, the Woods algorithm is originally used, I think, to allocate electricity among competing demands. It's kind of a physical system thing, whereas the McFadden thing is more of a human behavioral formulation. So it's kind of like it just depends on what you want to do, what you're trying to model. But obviously, we are often trying to figure out what people would do. So that's just a quick recap of what I failed to wrap it up with, because I was looking at the clock, is that George Backus would work a lot with Andy Ford, very well-known system dynamics person. And they would both sort of advocate using the McFadden approach. And this is a chapter from Andy's book, and I can't recall if I showed you this or not. I don't think so, but so Andy has a book on system dynamics and the environment. And in this chapter, he's looking at the various attributes that would make a particular car attractive to purchase. Instead of attributes of a city that would make it attractive to move to, right? Similar idea here. And so here we have in the chapter, rebates, fees, base price of the vehicle, purchase price, fuel costs, horsepower, range, fuel availability, and so forth, right? So there's these attributes, a list of attributes, and they got to be smeared together into a metric of attractiveness. And then you do that for each of the model cars. And then, you can see how the market is divided among the various, various types of vehicles. So you say, oh my gosh, how do you do that? And what have you. Well, he shows you how to do it right here. It's very simple, actually. And there's example, I don't want to go spend the whole time on this because this is sort of a wrap up. I just want to call your attention to it. Here it is, and it's actually quite simple to do. This is specifically for the vehicle example. And what he did do was he used the survey. He didn't do the survey, but he used this survey here that was done by these folks here at UCal, Davis, The Hague, and whatever. So these folks describe a survey they did when they're asking people about the attributes of a vehicle that they would want to buy, right? And here's the survey instrument is presented and what have you. And then he used that information in his model. Okay. So here is, I'm not going to take time right now. I just want to wrap this up. Here is Andy's thing done in Stella. I mean, in the book, it was done in Stella, but here's my version of it. Okay. So you can take a look at that. And that's, one of the various ways of allocating a scarce resource. And in this case, customers. There's only so many people looking for a car, right? And the various dealerships or automakers are battling for, they're trying to get 100% of the market, right? Okay, so this, I just want to make sure you understood that. Okay, so we press on. Next topic, learning curves. Okay, now what's this about? This is a little bit of a maybe a niche topic or something, I guess you might say. But what you'll see is we're getting into here diffusion models. There's a lot of issues when firms are trying to capture market share, or technologies or new products are diffusing into the market, and you're trying to get your new smartphone adopted, or your new electric vehicle, your new robot, or whatever the heck the product is, right? You're trying to win on, let's say, innovation, features, quality, and stuff like that, but also on price. And so learning curve strategies say, all right, let's try and make a lot of them, as many as we can, of the widget, and then get really good, really learn how to make them well. And then our per unit, our productivity will go up, and hence our per unit cost is going to go down. And we can pass that on in the form of a lower price to the consumer, and we can capture market share. Okay. So that's a common use of learning curves. You're learning by doing, it's called. All right. Now, how does one go about representing that type of thing in system dynamics? Well, I have my notes here, and a lot of times I'm like, I'm not going to type all this stuff up because this is just crazy. So we'll just go through my handwritten notes from whenever I took these notes. This is not a PDF. This is a picture. But just to go through this, if you don't understand the math, it's not horrible math, but there's a little bit of it. You learn this stuff in like pre-calculus class, logarithms and things. It's one of these things. My calculus professor, Dave Pankratz, used to say that would be teaching by intimidation. It's so because I say it's so without proof. So you have to like take my word for it. But at any rate, so here would be the cost, like the cost of producing a new widget, right? So you have some initial cost times, and there's a factor here. And E is experience with making the thing. And then there's some initial experience, okay? And there's a coefficient that is your rate of learning, or your shop floor people's rate that they learn how to make these things. Okay, so you have experience relative to your initial experience. Always good to normalize things, right? Make something dimensionless. And then you have some sort of factor here that tells you how quickly you're learning. All right, so there's a few assumptions here that are typically made of costs fall by a fixed fraction per doubling of experience. So every time I double my experience, there's my costs of making the thing fall by a fixed amount. That's an assumption, right? But Then when E has doubled, costs have fallen by the fraction F. Okay, so we're doubling our costs here, and we're cost minus fraction times cost. You're cutting them in half. So a 2 here is related on the left-hand side of the equal sign to 1 minus F times C. Now we're going to take the log of both sides. So you're just going to the natural log of both sides. Okay, and again, if you don't know what logs are, we needn't worry in this class about it. But if you're curious, go look it up.
It's a button on my calculator, I think.
Yeah, most calculators have a button, right? And then EN does it, right? So there's something with E and LN, right, going on, right? And we have E when we have exponential growth and things. All right, so we're going to take the natural log of both sides. All right, so as long as you do the same thing to both sides of the equal sign, we're okay. And then there's in pre-calculus, at least that's where I learned it. I think that's probably still the case. You learn rules of logarithms. Okay, so one of the rules here is you can pass the ln operator through here. It's a linear operator, right? So we're going to pass it through, and then we're going to add because it's multiplied here. Same idea here, okay? And then we're going to clean house. We're going to notice, aha, this is the same on both sides. We're going to get rid of it from both sides. Over here, we can cancel out the initial experience, so we're left with 2, right? And then we're going to rearrange here. We're solving for alpha. Why are we solving for alpha? Because that's up here. That's the learning rate, right? Okay, so there it is. So an example of costs fall by, say, 30% for each doubling of experience. You'd have to ask a manager that. Well, then 1 minus 30% is 70%. ln of 2 is 0.69. And you'd find out that you would put in your formulation in your SD model. What was it here? Minus 0.52 up over here. Okay, so you kind of followed that. Okay, cool, whatever. So let's look at an example of this in action. So some years ago, more than I care to admit, I think it was 1994. So that would be like 30 years ago. John Sturman and I were asked to do a paper for a book, a chapter in a book. And it was about evolutionary systems. And kind of the question was can system dynamics models evolve? They can change over time, but is it Newtonian change like the planets where they just repeat a particular dynamic, or is it Darwinian change where there can be mutations and what have you, and the species changes and that sort of thing? So we took on that challenge, and here's the model we came up with for the paper, the chapter in the book. To illustrate, there was obviously verbiage around it, and I think, bear with me, I think I have, let's see, do I have the paper here? Yes. So evolutionary economics and system. So here's the actual paper. If you want to read all the verbiage around it, you can take a look at the paper. But the model we came up with is in the book. And it's kind of an interesting model. So what happens here is, remember, the more you produce, so we're going to use learning curves. The more you produce, the more you learn about producing. And if you choose to use your gain in productivity, the falling of your per unit costs to try and gain market share by cutting your price because your costs are lower. Now you can say, I don't want to do that. I want to make more profits. But if your strategy is to take market share, then learning by doing and hence lowering your costs is one possible strategy. So the more you produce, this is firm one, it's producing more, and the stock is summing up or accumulating all of the widgets that firm one is producing. The more you produce, the more you learn, okay? And you can see here, firm one's unit cost, there's a learning rate over here, and it's the ratio of those two natural logs. See the ratio of those two natural logs right here is alpha, right? So that's right here. ta-da, it relates to something, right? And then so this is a little trickier here. It's not just the experience from the cumulative production, but it's also the firm can learn by appropriating learning from its competitors. So you can hire their employees and learn how your competitor's doing it. You can buy their product and reverse engineer it and see if there's any clever things that they're doing and what have you. Okay, so this is the cumulative learning that firm one can tap from their two competitors. Okay, we're not saying how they would tap it, reverse engineering, hiring, whatever. Corporate espionage, you hack their computers and look at their blueprints, whatever. We said we were silent on how they would go about acquiring that information. And that would be added to their personal knowledge. So the knowledge from others plus their knowledge is the total knowledge or experience. And then it goes into a learning curve. They choose in this model to lower price to try and capture market share, which makes their widget more attractive in the marketplace. Ceteris paribus, assuming delivery delay, functionality, perceived quality, and all that stuff are the same, or negligible differences to the consumer, then we're fighting for price. So this is more, I guess, like, I don't know, I'm trying to think of a good example, like gas stations, right? Gas is gas is gas. So this guy's gas and that gal's gas, I put them in my car, the car goes. So there's not really a difference in terms of, perceived functionality, perceived quality. Yeah, if my car knocks, the engine knocks if I put in this gas versus, but a lot of times it doesn't matter. It's like gas is gas, right? So a situation kind of like that. So now you're fighting on the basis of price, right? And then the lower your price is, the more attractive is your product. Okay, and there's a sensitivity that we have here and some randomness you'll see in a minute here. And then here's the aggregate attractiveness. So it's that most simple attractiveness formulation, or not attractive, well, that's what we call it, but it's that simple resource allocation thing, right? Where you have total demands and then the individual demands, and it 100% allocates everything. So it's that first one that it's this one here. So make sure we're nailing this down. Sometimes I know in my head what I'm talking about, but I can tell it's not clear. So it's this one here. That's what we're just looking at in the model. There's a lot going on here, but that's what's going on here. So you're saying, aha, we're using these formulations in a model. And then you're allocating the industry demand is just constant. Okay, there's a step, but it's just constant. So there's just a constant demand for this product, and the demand is being allocated among 3 competitors. And of course, the more demand it is, the more they make, and that's okay. Now, the firm 2 and firm 3 are identical. So nobody's given none of the 3 firms is given an advantage from some kind of structural difference. But the last twist on this is you can see the appropriability. So basically what we're saying here, you see firm 3 market share and firm 2 market share. So the stronger the competitors to firm 1 are, the more they're able to protect their IP, right? The more they're able to prevent firm 1 from stealing their employees. Oh, they offered you a higher salary, we'll match it and give you a bonus if you stay. The more they're able to employ, sophisticated encryption so their blueprints are secure, and so forth, right? So the bigger their stock is, the more filled it is, the more they're able to protect their knowledge from their competitors. And it's identical for all 3 firms. Okay, so what happens? Well, if you run the model, so we're just running it here, and you can, by the way, you can say, slow this thing down so we can watch it unfold. Sometimes people prefer to see things unfold. So you can actually, in the old days, you did everything you could to speed it up. You'd be like, it will be like watching paint dry, waiting for it. But now we want to sometimes see things unfold so you can slow it down. So in this particular run, so there's the randomness that's pinging the thing, right? You can see that there's an oscillatory tendency here. When firm 3 is up, firm 1 is way down, and firm 2 in this case is it's oscillating, but it's kind of business as normal. Sometimes we're up, sometimes we're down. Well, this time, the firm, that's 3 is green. It's kind of reversed, and firm 1 and 2 are doing the big swings. And you can see that one, the red and the blue are kind of the same. Now the blue and the green are kind of the same. And none is kind of in the middle and so forth. So it's different every time, right? So it's randomness that is driving, because the firms are all identical, right? And the sensitivities are identical and everything. So randomness starts pushing it this way or that way, and it gains a little bit of a advantage. It can protect itself, but then the randomness pushes it the other way and whatever. Okay. Now, what I didn't do in this case was, I better open the paper rather than trying to do it in real time here. What we said is, okay, that makes sense. That if it's a path dependent process, positive loops, right? So if it's very sensitive to that, then what would happen? I mean, is there any way for a firm to win in this situation? Of course, it's sideways. Of course. Seems to be going backwards too. But there is a way. Oh gosh. I thought we had a figure in there. Remember, I did this 30 years ago. Anyway, so what you can do, if you give one of the firms an advantage, an ever so slight advantage, it'll wipe out the other two. So if it learns just a little quicker than the others, over here, if I make this 9, let's see. Nope. Or let's make it 8-1. So ever so slightly give it an advantage. See if it works that time. That was not enough of an advantage. So let's see if we can. I can't remember what yeah, so I made it, instead of 0.8, I made it 0.85. And, there's a wipeout, right? Which one wiped out? Firm 2 market share. So firm 2 went, wait a minute. How did firm 2 win there? That doesn't make any sense. Should have been firm 1. It is firm 1. So we're back again. Anyway, I can't remember. So let me do that a couple of times. What did I say? 0.85. How about 0.83? That's stretching it out. That's kind of interesting. I haven't played with this model in quite some time. I say 0.85, so 0.84. How are we doing now? Certainly damping the oscillation. So let 3 win. So what if I'm going the wrong way? Yeah, so I was going the wrong way. So I made it 0.75. So instead of 0.8, so what if I made it 0.78 instead of 0.8? Yeah, see, you just give firm 1 ever so slightly a lead, and it can wipe out the others, because of course everything's based on the learning curve. What if I make it 0.79? Does it still wipe them out? No. So you need to, it has to be a little bit of an edge there, and it wipes them out. Okay. So that's kind of, it's kind of a little bit of a neat model, I guess. Play around with. Like I say, I haven't looked at it in quite some time, but okay. So so that's a paper we did with John. Here's the basic math. Now, John and some colleagues wrote a paper that appeared in the journal called Management Science, which is quite a prestigious journal. Hang on here, it's probably the #1 journal.
Can I ask a question before you run off?
Management.
Management Science Journal.
Mm-hmm.
Can that whole learning diffusion model also apply to like a service industry rather than product manufacturing, you think?
Sure, the more hours you spend doing a service, the better you'll be. The old saying was, who are the best doctors? Veterinarians, the ones who've seen the most patients, right? The ones who have the most experience.
We would like to think that, but it's determines whether or not they're really actively learning. There are some of them that are not. And
well, you know what? So then there's probably a decay.
Well, no, you get stuck in doing something that you're comfortable with. I mean, anesthesia, for example, you know, I'm stunned at the people that are doing anesthesia from 20 years ago when there's a lot better products, but it's, you know, they get stuck and they get comfortable and they don't want to change it. So, but I mean, I think the model is really great. It is making me think about, you know, how to improve productivity and better outcomes in a hospital situation or in public health. And it's reminding me a little bit of Senge's, you know, the 5th discipline, where he talks about the necessity of having a safe practice field in order to practice before you really throw yourself in there, you know, to actually do something new and different. And I don't know of a lot of industries or businesses where they provide that, especially when it comes to, you know, social skills that are frequently needed in service businesses. And now you have all these people that's been living on a cell phone, and you're getting them in, you know, to the workforce in their 20s, and they have, you know, struggle with their interpersonal skills. So I wonder how much that model could be adapted to accommodate those sorts of things.
Oh, I suppose anything where when you do more of it, you accumulate I guess an advantage, unless you're doing more bad things, then you're accumulating a bad thing, I guess. Well, yeah, so mathematically, this is how you do it, is, I guess, the sky's the limit, I suppose, as to what someone could apply it to. So in this paper, you can see here, they're talking about the strength of the learning curve, right, and all that stuff. So we needn't worry about all the details of this thing today. That's not the point of showing you this. Well, what I did want to show everybody was this. So when John and his colleagues submitted this paper, and I'm going to show you an example of this on Thursday at the doctoral seminar. You see there's an e-companion, okay, that they, a supplement that they gave to the journal, and it takes everybody, including the referees who they want to convince, and the editor, that, hey, publish our paper, through the model and all the results in egregious detail. So that, because you often don't have, particularly back in the day, you often don't have the space, you know, like, here's my 55-page paper. It's really good. And the editor might say, yeah, it's really good, but it's too long. You got to cut this down to 28 pages max. And so you're kind of skipping steps and proofs and stuff like that. But for the referees, you could produce, I'll show you an example of something I did years ago. Here's the paper for the journal, and here's for the referees, where I lay out every step, you know, so the referees can more easily follow things. So this is the same model laid out in much more detail. And then look at a table of all the parameters, initial conditions. So if somebody wants to reproduce the results, the sensitivity analysis that they did, replicating the simulations in the paper, see, very important. And they lay it completely out for, well, anyone, but certainly for the referees and the editor. You know, here's how we did it. There's no sleight of hand here, no data manipulation, what have you, right? And I think this is is super, super, super important to do. You don't have to do that. Nobody forces anybody to do that, but I just think it's a great idea. And when I've done it in the past, I've gotten remarks like, yeah, we're not going to publish your paper, but thank you for supplying us with all the details, because it made it so much easier to referee. And you'll find, again, I'll cover some of this on Thursday when we discuss refereeing, but particularly if the author is English is not their first language, it can be very difficult to understand what they're trying to tell you. And then they often skip steps because of space considerations and what have you. So you got to get from this equation to this equation or something, and you're like, I don't know exactly what happened here. And, you're tearing your hair out, and you're like, man, I'm not getting paid for this. I'm just doing this as a service, and this is killing me here. But if somebody gives you, all the answers or all the details, and then you can replicate the results, even better if they give you the electronic file and you can just run all the simulations. That's a really good thing. So I wanted to point that out. Okay. What else do we have here? I'm looking at my notes here. All right, diffusion models. That's the next thing here. Okay, so you might recall in 550, we looked at Jack Homer's model of the diffusion of new medical technologies into the marketplace, right? And I think we looked at the Bass model briefly. So the Bass diffusion model, let me just quickly go back to normal view. So the Bass diffusion model is one of those models that is commonly, like in every textbook, every software manual, every example. It's like, let's pick an example that we can show off our software or whatever. It's almost always the Bass model, because it's small. It has more than one stock. It has a positive loop and a negative loop and a nonlinear relationship. So it kind of has all the elements of a system dynamics model, but it's small. So if you're going to try and illustrate, and it's well known, if you're trying to illustrate, hey, pick my software package, here's the Bass model that you should be familiar with. It has all the stuff, right? So it's a very well-known diffusion model. And it was used originally by Frank Bass to describe how a durable good diffuses into the marketplace. Now, a durable good has an average life of at least 3 years. So it's not something like a hamburger. Well, maybe you keep your hamburgers for 3 years, but as soon as I get mine, I eat it, right? So it, in and of itself, it doesn't do a great job at everything. For durable goods, it was fine. But it's, it can be modified is what I'm getting at. So it's often the basis for lots of different things in system dynamics modeling, including not just the diffusion of a product into the marketplace, but the diffusion of innovations, the adoption of innovations and stuff like that. And it has kind of the same structure as the spread of a disease or the spread of a rumor. So you have those who have adopted it and those who haven't, and they interact, and the non-adopter becomes an adopter. So the person who hasn't heard the rumor interacts with the person who has, and the rumor is passed, or the disease is passed, or whatever. So it has the Bass model or its offshoots or its brother and sister models have lots and lots of applications in system dynamics. Okay, so it's in this category of generic structures called diffusion models. Okay, so so you might recall from 550 that this is the basic Bass diffusion model, or some offshoot of this. It more or less looks like this. Okay, so basically you have an advertising loop. And so just, if your advertising is effective, it starts pulling people out of here. Non-adopters are defined as those who have never heard of the good or the service, and they become convinced and then you're trying to convince them that they want to buy the product or the service, adopt the technology, whatever the case may be. And so the adoption rate is the rate at which they move from one category to the other. Now, this is the model is often also used to show the tricky case where this is a first order system. Even though there's two stocks, normally you count the number of stocks and that's the order of the system, right? But the stocks have to be independent of one another. And so the number of adopters here is initial adopters. What do I have here? I say 0. Potential market is the adopters plus the non-adopters. And the initial non-adopters is, what is it? 10,000, okay? So the stocks are related to one another, right? This minus the potential market is this, and vice versa, right? If the potential market is 100 households, 2 have adopted it and 98 haven't adopted it yet, they're non-adopters, then 2 plus 98 is the 100, and they're related to one another, right? Mathematically, they're related, so they're not independent of one another. So this doesn't happen very often, but just calling your attention to that.
So this would be classified as a first order system, even though it has 2 stocks in it because they're related.
Yes, they're not independent. That's correct. All right. So anyway, so there's an advertising effect here. Now, if we were to, do this, you should say, aha, that's molecule number 2 from 550, a first order negative feedback loop system with an implied goal of 0, just an ice cube melting on a hot asphalt driveway. Okay, and it's just going to, well, in the case of an ice cube, to the atmosphere or what have you. But in this case, it's the same structure, except we challenge the cloud, and the model, I should say, is keeping track of where it's not, water molecules, but it's where the non-adopters are going. They're going to become adopters. But mathematically, it's, if we get in here, it can be divided by the average lifespan, which is the same thing as times 1 over the average lifespan. So you can multiply or divide. It doesn't matter, right? There's first order control here, because when this is 0, this whole thing is 0, right? So if you remember that. So there's an advertising loop. Now, you could make this much more interesting when you talk about the effectiveness of advertising, because advertising is most effective when it's fresh, when it's new, when it's something you haven't seen or heard before. If it's a commercial you've heard 100 times, you tune it out, right? So there's a decay rate on the effectiveness of an advertisement, right? So, you could make it more dynamic and more interesting. And are you allocating money to your ads? And if you're not, are they getting stale and they're not as effective, and blah, blah, all that kind of stuff. But for now, it's just a constant to illustrate. And then you have the word of mouth adoption. Okay. So this is where you run into somebody, you interact with them who have already adopted the product, and they say, hey, I want one too. Now you might talk to them and say, it's like on Amazon, you read verified customer reviews, verified purchaser, and they say, this is the greatest product ever, whatever, it cured my baldness or whatever it's supposed to do. Or just the opposite. I never read the 5-star ones. I always read the 1 and 2-star ones, right? What if it sucks? Why? And if it's because, well, it was when I received it, it was missing a bolt. Well, that sucks, but that doesn't mean it's a bad product. It just somebody, it fell out of the packaging or whatever. But if they say, it broke and I used it twice, it broke, or, whatever, that's very powerful, right? At any rate, the point is you can physically meet somebody and talk to them about the good of the service, or you can encounter them or come in contact with them, let's say on a customer review, or it could be, you pull up at a red light and somebody else pulls up and you just observe their vehicle. You say, wow, that's a cool color. I want that color car. I want that model car. Again, you don't talk to them or anything, but you've encountered them, right? So the more the adoption fraction is, the bigger it is, the number of adopters relative to the potential market, everybody, which is this is adopters plus non-adopters, right? The more likely it is that you're going to run into them. So sometimes this is labeled probability of contact, probability that you're going to run into somebody somehow who already has the thing, right? And then, how many times do you run into them? Do you got one of these maniacs that does a customer review on Yelp and Amazon and for everything? They're constantly grinding these things out, or they don't do it very often, or they're a homebody. They don't go out and about very much, or they do, whatever. And then just because there's a lot of folks who have it and you run into somebody one way or the other, and they're out and about a lot, that doesn't mean you're just going to mindlessly adopt it, right? There's some chance that when you might not like the color or the features or the look of the thing, or, I think it's this, like the Cybertruck. Did you see this Elon Musk Cybertruck? People either love it or they hate it. So just because you see one, doesn't, and somebody says to you, wow, I love it. And, you might not like it, or you might like it. So there's some probability attached to that. Okay. So we have a positive loop. The more adopters there are, the more there will be. We have a negative loop because this box is just draining, right? When it's gone, right? And it's basically the two effects that are involved here. Now, for the the model is nonlinear, right? Because you get the current adoption fraction, which is adopters over adopters plus non-adopters times non-adopters. So you're multiplying stocks together. So of course, you've created a nonlinearity, and because it's nonlinear, there can be a shift in loop dominance. So the positive loop is dominating at the beginning and the negative loop dominates at the end. And the inflection point in this case is where the adoption rate is maximum. Okay. So hopefully you remember that from the first course. Okay. And, Jack Homer started with this and built this whole giant medical technology diffusion model. A lot of the interesting parts of it were that, well, the decision to adopt the cardiac pacemaker or a particular antibiotic was made by the physician rather than the end user, the end customer, if you will, right? So it's how do physicians get convinced that they should, use this therapy versus another therapy and what have you, if you remember all that. Okay. So as you might be guessing, this kind of formulation has lots of different uses in system dynamics. So I think it was mentioned a few times in here. We talked about one of the master students from China was interested in the battle between filtered water and bottled water and tap water in China. And so the problem was that, well, as people would recognize that let's say their river water was not very healthy, they would say, we got to get either bottled water or a water filtration system for usually an apartment, right? And so there was this battle between the bottled water people and the filtered water people, okay, for market share, okay? So here's new adopters. This is just the skeleton coming into the market. So this would be like you lived on a farm in the rural area and now you've come to the city and you're realizing the water is better in the country. So now you're in the market for a clean water source, or it could be young people forming a new household or what have you. Okay. So they're non-adopters. They're in the market for something that isn't dirty tap water. And they're either going to pick the filtered water or the bottled water. Okay, so there's an attractiveness thing between the two competing sources, right? And then, now you have the adopters of bottled water and filtered water, but they can switch. So if the other becomes more attractive, they can elect to switch. So, the problems with the filtered water was, well, you had to buy a machine and it had to be installed and repaired and maintained, and you had to buy filters for it and what have you. But the good news is once you had all that, you turned on the tap and the water just was there, right? Whereas if you wanted to go with bottled water, you were going to the store every week or every 2 weeks, whatever it was, and dragging these plastic bottles up, to your apartment on the 29th floor or something. Then you had to do something with empty bottles and what have you. And of course, it's it's fine for drinking, maybe washing dishes, but if you want to take a shower, you're probably still using the tap water and all that. So there's advantages and disadvantages of each. But the point is, notice the start was adopters and non-adopters. The intellectual starting point was the Bass model, but the Bass model wasn't adequate. But by the way, I forgot to point this out. With the traditional Bass model, Frank Bass assumed that when you became an adopter, you also bought the durable good. So an adopter supposedly is someone who hasn't heard about the product, and a non-adopter is somebody who hasn't heard about it and doesn't know they want it. An adopter has heard about it either through advertising or word of mouth and decided they want it. Okay, well, Bass assumed they also bought it. Now, for a durable good, that's fine. Durable goods last, particularly when he did it in 1969, a refrigerator lasted 20 years, a washing machine 25 or longer. I remember as a kid going in the basement of some of my buddies' houses for whatever reason, and the washing machine looked like it was from 1902. Those things were like indestructible, right? So there wasn't repeat sales. But what if it was like a hamburger? And there's a new hamburger place that opened up, and either you heard about it from your friends or you saw an advertisement and you said, okay, I want one of those. And you went and ate a good hamburger. And they said, that was great. I want to come here every Wednesday. Well, do we add a pipe here, a flow, and go back here and become a non-adopter for a repeat sale? No, because by definition, a non-adopter hasn't heard about it. You've heard about it, you just want another one. So there's a lot of inadequacies with this. So this is often like the intellectual starting point, but then you say, okay, I got to do some modifications here. So that's what went on with this thing over here. So we did push on and we went way beyond this. I just wanted to show you kind of, that was the Bass model led to that basic skeleton. And everything got fleshed out here, right? And so there was an attractiveness to switch sector and an attractiveness to initially buy sector and so forth. So what pipes they went down were a function of that McFadden attractiveness formulation. And the scarce thing that was being allocated was those in the market, right? Or if you're trying to convince somebody to switch over, right? So that was the thing that they were battling over. Switch, don't switch, or hey, you don't have either. You got dirty tap water. Pick our technology for delivering clean water. Okay, and there was other stuff we put in the model. There's an accounting sector, a pricing sector, and a bunch of other stuff here. But for the moment, the point is we started with the Bass model and the concept of adopters and non-adopters, right? And word of mouth and advertising. And we went from there. And we did have data. I don't know if I showed you this before. So you can see actual and simulated market share for bottled water. Bottled water is obviously winning big time. And here's filtered water. Wasn't as good of a fit, but it's still a pretty good fit. And we could run simulations like what should the filtered water people be doing to capture some more market share and what have you. All right. So this diffusion model thing is is important. It can show up in a variety of places, including the spread of a disease, spread of a rumor, as I mentioned. And we're going to be talking about the spread of Lyme disease or tick-borne diseases starting next time. So here's a hint. The infected ticks have to get an uninfected host, or an infected tick has to attach itself to an infected host and then attach to a dog and all. So this is going to be a starting point for the model that we're going to begin building, I think next week, if we complete everything today. Okay. All right. So what else is going on here? Let's look at this first. So Tom Fitteman, who I don't know if any of you ever met Tom, but he's a super good system dynamics modeler. And again, we turn our attention.
I met him in New Mexico at the System Dynamics conference there.
Okay, so some of you have encountered Tom at one point or no, or the other. But at any rate, there was a discussion about this topic. And he says, basically, I put together a little bibliography of important papers and such related to diffusion models. So I just included that. It's good, you know, if for a dissertation paper, you're going to use this structure, you want to make sure you highlight the biggies, right? Like here's Frank Bass over here. Because I can tell you, refereeing, if you get a paper that is really in your wheelhouse, like you've written in that area as the referee, which is why the editor says, oh, I'll have Mike do it. He's written in this area. One of the first things you do, you can't help yourself, is do what? You go to the back to the bibliography and you say, did this person cite me? And you also say, does this person cite the big famous papers, right? Right. So if they're not citing the biggies, you know, red flag goes up, like what's going on here, right? Now, that doesn't necessarily mean it's a deal killer, but you know, it's a very common thing. So it's always good to know the literature, particularly the biggies in your area, right? So you make sure when appropriate, you always cite, because that referees will always look for that. Are we covering our bases here? Are we familiar with the literature? Okay, so Jim Linus, another well-known system dynamics person. Actually, Jim was on our faculty at WPI for a bunch of years until he retired. He was roaming our hallways with the rest of us. He's a very, very good modeler. He wrote a paper some years ago called A Dynamic Model of Technology Diffusion. So this is not trying to get well, it could be a new product, a new technology into the marketplace, but it's not like you're trying to get somebody to buy your smartphone or your hamburger. There's an innovation thing going on here. And it's kind of neat. He goes through a number of tools and techniques have been developed to improve technology forecasting and assessment. For example, technological process or S-curves, and that's what's going on over here. So right away, you see an S-curve, you see positive loop, negative loop, inflection point. So there has to be some kind of nonlinear relationship, right? So I don't want, you can read the paper yourself. Cost experience curves, learning curves are in his model, integrated in there, right? So he's got something like the Bass model in there. He's got something like a learning curve formulation in there. Price performance curves, diffusion or product life cycle curves. So this is more like a Bass model versus this is a twist on it for technology diffusion. The Fisher-Pry technique. What the heck is that? A means of estimating a substitution curve based on the assumption that the rate of substitution is proportional to the fraction of the older one still in use. So you have an installed base of something, right? And you're trying to get people to stop using the old one. and start using the new one. And they're like, oh, but my old one still works. You got the people running, Windows XP, right? Or whatever, right? So management is interested in affecting the substitution curves to the company's best advantage through the decisions regarding how much to spend on developing the next generation technology versus improving the performance of the current technology, the current generation. When to introduce the next generation, how to price the product, and how much to spend on marketing, right? So those are all important questions, right, in this area. So Jim presents a nice little model here. Without getting into all the details, you can read the paper. He's very talented, right? And somewhere he's summing up. Okay, so further work, further sensitivity analysis, case studies, and application, whatever. So anyway, so I thought that was a nice paper that related to this stuff. I think Jim will be very interested in this paper. I don't know that he's familiar with it. And then finally, in this area, I have a comparison of diffusion models, because I think I mentioned that there's a bunch of these things. So I asked ChatGPT to assist, and I said, compare and contrast the following growth and reliability models. So from my notes, I don't remember where I got them, probably at MIT. They said, here's a list of these S-shaped growth models, and they have advantages and disadvantages and what have you. And so I said, well, I could look up each one and try and figure it out, or I'll just ask ChatGPT to summarize them for me. So I'm not going to, you can read it on your own. It's just that, we want to just call your attention to this. But so here's what it came up with, because I said, compare and contrast these models. Okay. So here's the Bass model, right? Focuses on adoption. The logistic model describes S-shaped growth. Gompertz model, asymmetric S-shape. So the first part and the second part of the S are not symmetric. Okay. Gompertz, I guess that's asymmetric. Sorry. Weibull, primarily a failure time model with variable hazard rates, depending on a shape parameter, well suited to reliability studies. Don't know exactly what that means. That's not really my thing, but I thought I'd present it anyway. Negative selection reliability life models focuses on system reliability. Okay, but they all have this distinctive shape. The Harvey model, assuming it was somebody named Harvey, it's more sort of a time series thing. And extended Riccati model captures complex nonlinear growth or decay dynamics and is particularly flexible for modeling interactions in fields like physics, economics, or biology, where standard linear models fall short. So I would be like, okay, if the Bass model isn't getting it done, this might be a place to look, right? Then it starts saying, let me give you the math. So here's the extended Riccati, and it put in these stupid slashes here. But remember in the first course, when we took Lotka-Volterra, and we took the Richardson arms race model, and we said, oh, look at the math. It's right out of calculus class. But wait, we can translate these things into system dynamics, right? It turns out it was pretty straightforward. So that is going to be what? A ordinary differential equation, right? So the change in something called n, right? N would be a stock. So the change in the stock named n is a parameter times n raised to the second power plus b times n plus c. So not terribly, it's a quadratic, not terribly sophisticated, but there you go. That is not hard to model, right? It's a flow equation. Let's see. And then what do we got here? Symmetry and saturation behavior, it tells us about. Applications and suitability by field. Where might you use these things? Parameters and their interpretation. Okay, good to know. Okay, so the parameters for this Riccati thing, A, B, and C, offer flexibility for interaction strengths, nonlinear growth or decay. Yeah, that doesn't tell us a whole lot there, but okay. Strengths and limitations. And in summary, okay, so then it tries to sum up for us here. Okay, so anyway, I just thought that was kind of fun to say, is the Bass the only starting point here, or are there others? There are others, and they have apparently strengths and weaknesses. And if one of these things is going to be in your model, or part of your model, you might want to investigate alternative formulations of their strengths and weaknesses and what have you. And again, it'll become consistent with the literature. In fact, I'm looking at my notes here. Yes, so I want to go back to John's because I didn't make this point. So remember, I was talking about how Sturman presented this, and his colleagues presented an appendix, if you will, companion to go to the referees and the editor, but then I'm sure they put it on the website and what have you to make it easier to follow the discussion. So notice what's going on here. John and his colleagues are not presenting system dynamics equations, dynamo equations, right? Let's see, do I have an integral sign here somewhere? I'm not sure what he did here. I can't remember. They're all presented as ordinary differential equations. Sometimes he throws in an integral sign, and I'm not seeing it here. But at any rate, what he and his colleagues are not doing is they didn't do this. They didn't come up here and say equation viewer and say, show me all the here's all the equations, right? Let's turn off some of this stuff here. So he didn't do this kind of thing, right? The old dynamo sort of Euler's equations. Instead, they developed the model this way, but then they said, all right, for the referees who are not typically system dynamics people, right? They're going to go, oh, I don't understand these bathtubs and faucets, or that looks like a toy with those icons, or, oh, that must be the limits to growth. That was wrong, or whatever, right? So you get human nature being what it is. You get biased editors, biased referees, whatever. So a skill that is good for doctoral students to learn who have to publish in peer-reviewed outlets is to take your work, develop the model traditionally in system dynamics, right? Here's a flow equation, right? And then learn how to write them or rewrite them in more traditional math, right? And that way there, somebody who's wired that way, learn to do their thing that way, will be comfortable. Notice there's no stock flow diagram stuff here, right? Nobody knows except us, and John and his colleagues, that the model was developed with system dynamics, right? So it's just, I had one experience with a very, very famous economist who read one of my papers done with system dynamics, stocks and flows and feedback loops, and sent me an email and said, Mike, I read your paper. I have a bunch of questions. Would you please answer them? And I answered all the questions. And then as I'm answering the questions, I'm thinking, I don't think he understands the model. So I said, by the way, in case this is helpful, here is my model rewritten in a more traditional format. And I wrote out the differential equations and all that. And he writes back, he goes, oh my God. He goes, I understand now what you're doing. I didn't realize you had those weird square thing diagrams. I didn't understand it, but now I understand. This is great. Da, 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 da. So it was like, it opened his eyes to what I was doing. And he was being polite and he's asking questions. He's trying to understand. But until he saw it, I was writing in French and he didn't understand French. He understood German. And when I switched it to German, he understood. So again, just tips for getting your work published in peer-reviewed outlets. You have to sometimes tailor. Now, for the SD review, you don't have to do that. But for management science, they felt that they had to do that. All right. So let's move this out of the way. Shrink that down. What else do I got here? Attribute, ordering, diffusion. All right, last kind of topic for tonight, discrete formulations. I think we're going to get through everything and we can start working on a model next week. So I do have a PowerPoint here somewhere. And let's take a look at the PowerPoint slideshow here. So when traditionally trained scholars, let's say in the social sciences, people who worry about systems with people in them, whether it's military science, management science, economics, sociology, political science, psychology, anthropology, environmental studies, whatever. When they do dynamics, they traditionally either use difference equations or differential equations. So when we do system dynamics modeling, we use differential equations, ordinary differential equations, not partial differential equations. If you hear partial, no good. That's not what we do. It's ordinary differential equations. So we're doing a math thing. Now, heretofore, the math has been pretty simple. I mean, we threw a couple of natural logs at you today. We didn't really delve into what they were exactly, but you know, and I think in the first course I threw an E at you and a couple of maybe one integral just to show an exact solution. But by and large, you can do system dynamics at quite a high level by knowing arithmetic, right? Because we're not analytically solving these things. We don't have to remember polar coordinates and Cartesian coordinates and the derivative of sine is cosine and all trigonometric functions and all that stuff from calculus class. That stuff has its use. It's perfectly fine. But Forrester brought our attention away from obsessing about the math techniques to obsessing about what is the important structure of a system that causes its behavior, right? So having said that, that's us. Traditionally, you know, if you're doing dynamics, you were doing difference equations or differential equations. And technically we're doing ordinary differential equations. Now, my brothers and sisters in economics almost always use difference equations, not differential equations. They use discrete time formulations. Why? Well, it's one of these path-dependent things where that's just how they started doing it. And they taught their students to do it, who grew up and taught their students to do it, who grew up and taught their students to do it. And then the people doing it got on editorial boards and wanted to see that, or they wouldn't publish the paper. Well, you get the idea. Also, the primary reason they probably did that, we don't know for sure, is that economic data are released according to a well-defined schedule. It's called the economic calendar. And because the release of economic data, usually macroeconomic data, will move financial markets, not always, but sometimes a great deal, the data have to be released according to a well-defined schedule to everybody at the same time. You might have remembered the movie Trading Places with Dan Aykroyd and Eddie Murphy and Tony Curtis's daughter. What's her name? Forget her name. And Don Amici and Ralph Bellamy, famous movie, where the two older brothers, Don Amici and Ralph Bellamy, made a bet that they could take somebody from the street and teach them to be a successful commodities trader. So they took Dan Aykroyd, who was this uptight commodities trader, and they nefariously got him fired. And then they took Eddie Murphy from the street and put him in his position, right? To observe, to see if Eddie Murphy could do the same job as Dan Aykroyd, who was Ivy League trained and all this stuff. So it's a comedy and whatever. But in the movie, these brothers doing this terrible stuff are scheming to make a ton of money in the commodity markets by getting a crop report ahead of the rest of the market by stealing it. And then they can put on a position. And then when the rest of the market, rest of the people, commodity traders find out about it, they'll push their position to new heights. And of course, Eddie Murphy and Dan Aykroyd find out about it. They scheme together and they foil the plot and all this. So these data move markets. And because they are released according to a well-defined schedule, the thinking is that's why economists back in the day adopted discrete dynamic modeling. So again, if we're trying to talk to economists or those who do discrete modeling or get a paper in a journal where that sort of modeling is favored, we want to be able to deal with that, right? To either replicate their results and say that, you know, it's no good, or at least present our stuff in their format if that makes some level of sense. All right, so we continue then. So this is a bunch of hoochie coo about how you do traditional difference equation modeling, discrete time modeling that they do in economics. Don't worry about the details here, other than to note that what it boils down to is, and my cursor always disappears. Modeling. Cursor is on this one, but it's disappeared on this one. I don't know why that is. So let's try this again. You can see my cursor. Here we are. Other than to note that the value of something today is a function of its value a period ago, 2 periods ago, and so forth. Okay, and then there's a bunch of math that happens that we needn't concern ourselves about, and you can analytically solve this linear difference equation system, this second order linear difference equation. We don't need to worry about how you do that. It's all crazy. But let me give you an example on how we can reproduce that kind of thing in system dynamics, even though it's discrete dynamic modeling and we do continuous dynamic modeling. Okay, so here's a very, 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 very famous model that was done by Paul Samuelson. Paul Samuelson is known as the Einstein of economics. He was the first American to win the Nobel Prize in economics. And among his many accomplishments was he wrote a textbook in 1947 that became the template for every modern introductory economics textbooks. It's like the Gray's Anatomy of economics. Everybody, well, Samuelson has passed away for a while now, but when he was living, everybody studied Samuelson's economics or another book that patterned itself after Samuelson's economics. McGraw-Hill had to give him stock in the company because he was earning so many royalties from the book. So Samuelson, super famous economist, and he was famous for many things, but one thing he's super famous for is this paper where he presented this model. It's a macroeconomic model. So basically what's going on here is this is GDP. Y is GDP. And it's the sum of spending by the household sector, the business sector, that's investment spending, and the government sector. The government sector spending in his model is just 1. By the way, he did this in 1939. So if it's not the most realistic of models, we're going to cut the guy a lot of slack. Spending by the household sector was some fraction of their last paycheck, their last aggregate paycheck. So they got their check on Friday, the end of last week, and this week they're going to spend some fraction of it. 1 minus alpha, they'll save, not spend. And then investment by the business sector is the change they're observing, business people are observing in their customers' spending habits, which is the household sector. The household buys from the business sector. So as if C now minus C last time, if the household sector is spending more now, they're going to invest more in plant and equipment to make more stuff and vice versa. Okay, so to solve it with system dynamics, we're going to substitute 2 into 3. Okay, when we do that, we get this thing over here. So we're going to stick 2 and put it into 3. So that goes in here. Alpha times YT minus 1 goes in there. And then we're going to move the 1 to a 2 and we put it in over here, right? And then we're going to substitute 2 and 4 and 5 into 1. So this is now I, right? So we're going to substitute 2 and then 4, and then the new thing in here, the new investment function into 1, and a little bit of goofing around. And you see we get that second order difference equation where the GDP now is a function of GDP before and then 2 periods before. Okay. And there's an appendix here. If you want all the nasty details on how you solve it, you can look, but don't worry about it. But can we use system dynamics to figure out what's going on here? Here's how you do it. Here's the trick. I have not seen this trick done anywhere else. I'm not saying I invented it, but I haven't seen anybody else do it. And I've seen people do it different ways. So I might be the person to figure this one out. I don't know. I'm not trying to brag. I'm just saying I haven't seen this done anywhere else. But the way I figured out how to do it is to remember infinite order delays. Because remember, when economic data is released according to a schedule, right, in between the release, nothing's happening. There is no data in between. There's data point, data point, data point, and then nothing in between, right? So how do we make it do that? Well, infinite order delays do that. Okay. So can we use infinite order delays to get us there? People who have tried to figure out how to do this, because we're using continuous modeling software to do discrete modeling, right? So how do you do that? People have tried to use a DT of 1 to do it, and that kind of gets you there. But I think it has problems because you have integration error issues. So my method doesn't require you to have a large DT, a DT of 1, and you can use any DT you want. So here's what I did. So I have YT, and here's the equation. It's C plus I plus G. That's the same thing as you just saw, right? So C, I, and G. And then I lag it. YT minus 1 is just a material delay, infinite order delay, right, of 1 period. So it's YT minus 1, right? And then that goes into alpha times alpha times YT minus 1 is spending by the household sector. Then that gets lagged, right, with a first order infinite order material delay, right? And then investment spending is beta times the difference between this household sector spending now and before. And when you run the model, you get this. So you don't get the smooth thing over here, which some people who do difference equation modeling, you'll see, even though it should look like this, the software is connecting the ordered pairs and it's smooth. And every time I see that, it's confusing because it's like, it's not supposed to do that. You're using difference equations, but maybe it's because you're just the software package you're using, it is just programmed to go between points rather than, I don't know why it doesn't, but at any rate, this is the proper way to do it. So hopefully everybody is seeing that is that. Now notice there's no stocks. Now there are. So in Stella, you can go up here and say, give me a delay converter. So that's a circular icon with a square in it. And what that's telling you is that that converter has a stock inside of it, or at least one stock inside of it, right? Because if you have a delay, stocks create delays, right? So if we were to look in here, you can see that we have the delay function in here, right? So stocks create delays. There's implicitly a stock in here. Okay, so you can see the feedback loops rather nicely, and you can see the run here. Okay, so perhaps it's a little off-putting to not see the standard stock flow thing, but remember, we're using continuous time software to make it do discrete time dynamic modeling. So we're kind of horsing it a little bit. Okay. Now, Samuelson in his original paper presents different runs where he says, well, if you make alpha and beta these different values, here's what you get. He gives you the numbers, literally the numbers. And then he says, here's alpha and beta. There's regions where if you change these values, you get different behaviors. So you can test to see if that's entirely true. If alpha is equal to 1 over beta, you're right on this line here and so forth. And you get different behaviors. And he tells you in the paper what the behaviors are. So what I did here is I just said, let's replicate his results from his super famous paper. Every student of economics is familiar with this paper. Right? And you can see that, you know, he's doing it with I guess we call it a bar graph or something. I'm not sure that was a 1939. It wasn't really a computer generated simulation. Mine is, but you can see, you know, the pattern is pretty much the same, except wait a minute. His white bars here, it says government expenditure, but it's not, it's GDP. So that's an error in this very famous paper. I've never seen anybody catch that one. And also, I think spending by the household sector, C, is a little strange, right? It goes from 0 to 1, 0 to 1.1 is here, where the blue line is. This is 0.5. Then it goes to 1. So I'm not sure that now Samuelson's a Nobel laureate. He was a genius. I'm sure this was a printer. These mistakes were printer errors, not his doing, that he didn't understand this and I do or something. I'm not saying that at all. But again, note the importance of being able to replicate results, right? You can tidy up things. You can see if things are tight, right? And sometimes you can find mistakes. Now, Suleiman Ba, our recent PhD in economics and system dynamics in May, was familiar with what I just showed you. And he said, I don't like the fact, Mike, that you do this, that you have stocks in there, but you don't show them as stocks. And I said, well, that's sort of a feature of the software. So he said, I'm going to see if I can fix that. So he came up with this way of doing the exact same thing, but now you can see the stocks in a more traditional format. Now, it was clever. It's very good. Now, in order to do that, however, he has to, if you open up the molecule, you'll see he's still using those infinite order delays like I did. So it doesn't absolve you from using the infinite order delay, but now the visual presentation is more familiar to SDers. So cool, you know, kudos to him. Now, among the things he did for his dissertation was, if I can find it, he came up with a way to take elements in a system dynamics model that are continuous, that are flowing over time, and make them discrete. Now you say, why in the heck would somebody want to do that? Isn't the point to acknowledge that time flows continuously like a river, and we're trying to, you know, simulate that and mimic that and what have you? And the answer, of course, is, well, yes, although there are times when a discrete formulation is called for. But also, again, if we're trying to talk to people in other fields who are familiar with discrete stuff, right, a way to gain their confidence, one element of gaining their confidence, is to show their stuff with our tool. So I'll say, hey, I can replicate your stuff. Don't worry, we're not doing some weird thing here. We're tight with you. We can exactly replicate your stuff. So if we want to use an otherwise continuous model that has a discrete thing we're going to stick in there, let's say something from behavioral economics, the behavioral economists tend to work in discrete time. And we're saying we're going to put a behavioral economic psychological thing into our otherwise continuous system dynamics model. If we want, and we send it to the Journal of Behavioral Economics, we got to be able to show that, hey, we're not doing anything weird here, right? Here's a replication of your stuff. So it should be legit. So Suleiman came up with this formulation for his dissertation. it's quite good. So this is equilibrium here. If you remember the little molecule I built for test inputs. But if we go to one is a step, right? So there's not much of a dramatic change there, but is what it is. 2 is a pulse. So you can see instead of sort of a triangular peak, now it's got that distinctive sort of flat roof. So 3 is a sinusoid. That's right. So now you can see more clearly the discrete stuff happening. 4 is noise. Again, you can see it, we can run it. I think there's no seed. It's different every time. Anyway, 5 is linear growth. You can kind of sort of see it here, stair stepping. And 6 is exponential, and you can see that a little more clearly. So if we need to go discrete to feed into something that would satisfy somebody else, a discrete formulation, maybe it's going to satisfy us for all I know. There's a way to do that. Okay. Now, one thing that I noticed, and I got Suleiman to work on for his dissertation, was back in the day, economists and others wondered how does a discrete time and a continuous time model of the exact same thing compare to one another? Are they identical, except one is more stair-stepped and the other's more smooth, or are they substantially different, or what have you? So we found, we have a book chapter on this. We found a paper by some Russian, I think they were mathematicians, but they were doing economic modeling and saying, can we directly convert a difference equation model to a differential equation model, a macroeconomic model? So it's being worked on today, but it was also worked on in the 1950s when after World War II, macroeconomics was coming into its own, dynamic modeling was coming into its own, and there was this pivot where macro data was being figured out. How do you measure it? And they started saying, let's use discrete time and all that, because the data are released according to a schedule. Some well-known economists back in the 50s were writing books where they were looking at the same model done with discrete time and continuous time and presenting them side by side. So I asked Suleiman for his dissertation to take some of these famous models and see what he could do in the system dynamics world. So here's Samuelson's multiplier accelerator model, as close as he could to getting it directly converted from one to the other. The paper has there's a bunch of nasty math to make it happen. And then on the microeconomic side of things, there's something called a cobweb model. Now, a cobweb model is so called because if you have a supply and demand curve, let me get out of here just real quick so you can see a little bit bigger. So, supply and demand are two lines crossing at a point, supply curve and a demand curve. And if you have a change as it goes from demand and supply, it'll go like that, spiral around if it's a stable system. And it looks like a spider's web. That's why they call it a cobweb model. So Dennis Meadows' doctoral dissertation was taking the cobweb model and then saying, let's redo it with system dynamics. And then he made a generic structure, and then he applied it to the chicken cycle and the cattle cycle and the chicken, cattle, I forget what, like 3 different commodities, agricultural commodities. So the cobweb model is very famous. It's a famous micro model, and there's various versions of it. So here's one. I don't know if Suleiman did this one or I did, but you can PowerPoint is so picky, I'll tell you. it doesn't want to let go when it doesn't want to let you out of it. But you can see here, we couldn't get it to spiral inside of Stella, but the order, it would be going from these ordered pairs around the horn here, but you can see it settling down to an equilibrium of price and quantity. You have quantity and price on a Cartesian plane here. This is a Marshallian demand curve and all that. So standard Econ 101 stuff, right? And then Suleiman said, I prefer my meaning his technique representing the stocks and flows explicitly. So, okay, we got that in there. And then he found it was hard to exactly replicate that particular version of the cobweb model. So he found another one where he was able to replicate it in discrete time and then in continuous time, almost exactly. So here and here. Okay. All right. Now, why am I asking him to do this other than, well, geez, that's interesting or not, depending on what you find interesting. And we get into this area more broadly of when do we add, or when is it okay to add discrete formulations to system dynamics models, and how do you do it? Do we want to convert a discrete model into its continuous form and add, or formulation, and add it to there, or leave it as discrete and put it in, or make it discrete inside of the continuous? You know, this is an issue, right? And I don't think there's there wasn't a good answer, which is why he did this for his dissertation work. I think the discrete continuous dichotomy is the most misunderstood thing in system dynamics. Like, what is DT, right? And how does it work? How does it relate to continuous time modeling? And if we're using DT, where the computer is taking discrete steps in time, aren't we doing difference equations? Well, in a sense we are, but we're using difference equations, if you will, to approximate the differential equation. We're not using difference equations to do difference equations. And if we want to do that, it's not, you don't just make DT of one. You've got to do a little bit of fiddling. So it's a very misunderstood area of system dynamics, I think, possibly the most misunderstood area of system dynamics. So what in the paper I wrote, in system dynamics modeling, it is quite common to add a discrete time structure or molecule to an otherwise continuous model. For example, minimum and maximum functions, pipeline delays, infinite order delays, boxcar delays, ovens, conveyors, queues, and first order control structures that include the model's time step in order to prevent the last entity leaving a stock from pushing the stock into negative territory. These are routinely added to our models. So it's not like, it's like, oh my gosh, don't add a discrete thing to your continuous system dynamics model. We do that all the time. So then I go on. In light of the openness of the modern system dynamics paradigm to adding discrete structures to otherwise continuous time models, I think I mentioned last time that Forrester in his Principles of Systems book says you cannot have DT in a flow equation. Yeah, you can. A natural question to ask is whether or not it's possible and profitable to replicate discrete time structures from behavioral economics and integrate them into a system dynamics model. So I think where our field is weak, or at least one of our cutting edges, is instead of taking a normal parameter and modifying it with pressures from elsewhere in the model through table functions, that's the traditional way of doing it, can we represent what psychologists and behavioral economists know that people do when they make dynamic decisions, with all the warts and all? Can we identify what people do? And really, it's identify what others have identified that people actually do, and put those structures into our models in a manner that would be acceptable to a psychologist, mathematically oriented psychologist, or a behavioral economist. And how do you do that? Now, what does Jay say about this area? Well, we go back to industrial dynamics, which is to this day still the original Bible of system dynamics, right? And Forrester wrote about this. He says, In formulating a model of an industrial operation, we suggest that the system be treated, at least initially, on the basis of continuous flows and interactions of the variables. Discreteness of events is entirely compatible with the concept of information feedback systems, but we must be on guard against unnecessarily cluttering our formulation with the detail of discrete events that only obscure the momentum and continuity exhibited by our industrial systems. These comments should never be construed as suggesting that the model builder should lack interest in the microscopic separate events that occur in a continuous flow channel. By studying individual events, we get a picture of how decisions are made and how the flows are delayed. The study of individual events is one of our richest sources of information about the way the flow channels of the model should be constructed. The preceding comments do not imply that discreteness is difficult to represent, nor that it should be forever excluded from a model. When a model has progressed to the point where such refinements are justified, and there is reason to believe that discreteness has a significant influence on system behavior, discontinuous variables should then be explored to determine their effect on a model. No other than Jay is saying, hey, you can do this. What does David Laibson say? He's a Harvard economist who does behavioral economics. So in his famous Golden Eggs paper, here's what Laibson writes. A second problem associated with his model, the Golden Eggs model, is the anomalous prediction that consumers will always face a binding self-imposed liquidity constraint. For example, the Golden Eggs model predicts that after making this consumption choice, consumers should have no liquid funds left in their bank accounts. This prediction contradicts many consumers' experiences. However, this problem can be readily addressed by introducing a precautionary savings motive for holding liquidity, for not spending everything you have. For example, consider a continuous time analog of the Golden Eggs model, which is very famous among behavioral economists, and assume that instantaneous liquidity needs arrive with some hazard rate. Then in equilibrium, the consumer will only rarely completely exhaust her liquidity. So he is one of the big cheeses in behavioral economics, and he's saying, yeah, we work in discrete time, but it's okay to consider going to continuous time. Forrester is saying we work in continuous time, but it's okay to go to discrete time. So we got big cheeses saying, hey, it's okay, like, calm down, it's okay, don't be afraid. All right. So we had Suleiman looking at some stuff for his dissertation. So this is coming from, there's one of these figures in the Golden Eggs paper, but we replicated one from a paper by somebody named Rasmussen. I don't remember the guy's first name. But here's it replicated in discrete time. Now, here's the thing. It's a discrete time formulation, but look at how it's presented here. This is what I was saying before. You'd look at that and you'd say it's continuous time, right? But it's in discrete time in this paper. So the proper way to do it is this way, right? But they do it this way. These people are not idiots. So I'm sure it's just the plotting program they use or something like that. But I think, this is how it should look. But is it possible to, like Suleiman converted the discrete time Samuelson model, the discrete time Cabot model into its continuous counterpart? By the way, there's the equations for this. And the answer is yes. It's actually quite easy. This is continuous time version, which is matching theirs, although theirs was done in discrete time. Okay. So I'm not entirely sure what that means, other than I think one of the cutting edges of our field is in learning the behavioral economic psychology things that people do when they make their decisions, particularly in the face of uncertainty. They're not sure about something, but you still have to make a choice. And there's all sorts of things about present bias and prospect theory where you attach more negative utility or satisfaction to a $100 loss than you do positive satisfaction to a $100 gain. It should be symmetric, but it's not. People don't want to lose. They dislike losing more than they appreciate winning. It's called prospect theory. They anchor and adjust. We've looked at that with expectations. And, so on and so forth. Identifying all the stuff that people do in general, and then in specific areas, and then replicating the well-known papers or results in system dynamics, which are almost always discrete, and then knowing how to bring them into our otherwise continuous models, or converting them into their continuous counterpart and showing that they're the same, and then putting them in our models, I think is one of the cutting edges of our field. And, something that doctoral students should be aware of and consider working on as part of their research program, because bringing these formulations into our models will enrich them way beyond, here's the normal parameter and the effect of A and the effect of B and the effect of C with table functions. And it's like, oh yeah, the normal birth rate goes up when the GDP is higher. Oh, okay, but there's no why there. There's no decision-making that people are doing. Presumably, people are deciding to have children in that example, or spend more, or whatever the case may be, but there's no human decision-making in there. That's a traditional Forrester way of doing it from 1961 or even preceding that, I guess. And that's fine. And you can do it and it works. But can we do better? Can we enrich our models such that they will be seen, well, more interesting just in general, but then more digestible to people in the other social sciences we have to convince to accept our results? Not just, hey, great job, Mike, I liked your model, I now understand it, but they start changing their behavior or changing policies because they believe the model is telling them something, right? They got to accept it, right? And they got to understand it and be comfortable with it. They want to see their stuff in there, right? So I think that's becoming comfortable with the discrete continuous thing is part of that battle. Okay. All right. So why don't we leave things there? That's kind of the end of the generic structures and molecules I wanted to show everybody. We've been at this for quite some time, right? I don't know how many sessions, and there's a lot of them, right? Certainly not all of them. There are many more. You can, look at Jim Hines's paper. He has a whole boatload in there, and Stella has assemblies and, what have you. But these are formulations, generic structures, molecules, whatever you want to call them, that I have found useful in my work. And so I give them to you. It's not a comprehensive list of all of them. You might not find them useful. You might make your own discipline-specific category of these things, collection of these things as you go along, which is perfectly fine. But hopefully already you've seen stuff previously presented being joined together. And then as we go along, you'll see more of that as we're building a model. Now, we're not going to build a model starting next time we're going to use every single one of the molecules and such. Damn it, just to use them. We'll use them if it makes sense to use them. And if it doesn't make sense, well, I mean, we're not going to throw it in just for the sake of throwing it in. But, hopefully you'll see the process of using these things to assist us in what we're doing.
So before we get off tonight, I was wondering if you would mind looking at one of the models I'm trying to build on the topic of generic components.
Yeah.
Before we get off the meeting tonight. I don't know if this is going to benefit anybody else, so I don't want to take up everyone's time.
Yeah, sure.
Okay.
We'll see what we can. Is this a Khalid model of some sort?
I have to go, you guys. It was good.
Okay.
Thank you.
See ya.
Oh, it's saying I can't share.
Oh, sorry. How to make it. Let's see. What they do is they change. Oh, here. Maybe. How about now? When they have a new version of the thing, they sometimes put the things in different spots. And it's like, I don't know where it is.
Okay, I think